Hi, this is Tim. Testing video. Up, down, right, and left, and audio. All right, we're here for the 5th attempt. Thank goodness I'm not a person that likes to get angry. So, first, I deleted one. I had one with no audio. Upload crashed. And the most recent one, total fuzzy, out of focus. I don't think there's much more that can go wrong, but we'll give it a try. We are doing conditional probability. Conditional probability is written this way. Some event in a universe is been given, and you're calculating a probability based on that given fact. Let me do an example of it with a tree. We'll walk through it. So I'm going to give you some outcomes. Not all outcomes are possible. There's an A, B, and a C, and that's it. And we're going to do them repetitively. So here is the start. I'm going to make a little tree. So first off, when you start, you have the possibility of outcome A, outcome B, outcome C. Oh, I'm going to make a D in here, and an outcome D. Now the probability initially of an outcome A occurring is 1/3, 1/3, 1/6, 1/6. So notice, in your first movement in this experiment, you either get A, B, C, or D, but now we repeat forward. Now, if you got outcome A, there are only 2 things that can happen next, a B or a D, and they're equally likely. If you get an outcome B, there's only 2 things that can happen, A or a C, and they're equally likely. If you get an outcome C, why 3 things can happen. You can have an A or a B or a C again, and they're also equally likely. And then lastly, if you get a D, you can either get an A or a C, and I make these equally likely as well. So this is a game. It could have different rules. This is how it proceeds. Now I'm going to ask a question. What is the probability that on your second trial, that means you made it down to the bottom, you get an outcome A, but given B or C has occurred? Well, I'm going to do it, calculate it from the tree here directly. So first off, we're allowed to follow down B or C as an initial occurrence. So this is where we start. And we're interested in A, so here and here. So it appears that on the face of it, we have a 1/3 times 1/2, that gets you here. And you have a 1/6 times 1/3, gets you here. But we are told you went down this, so there are other outcomes in this part of the tree, and we should really realize this is our universe. The only thing we know happened is we've gone down this tree. So in our limited universe, we're interested in these probabilities, but I want you to notice that your limited universe doesn't have a complete probability of 1, because the limited universe has a 1/3, 1/2 to reach here. It has a 1/3, 1/2 to reach here. It has a 1/6, 1/3 to reach here. It has a 1/6, 1/3 to reach here. And it has a 1/6, 1/3 to reach here. So your universe has a set of probabilities. If we added them up, They don't add to 1. But if that's all we're allowed to look at, well, we can adjust this by normalizing it. We can divide by that number, and now it is the proportion of this probabilities to all of them. And that's a nice calculation. It understands why we divide by something. It's called a normalization. So you've seen normalizations before. Suppose you integrate a function and the answer is 5/6. Well, we can adjust that function, f divided by 5/6, and now the integral of f hat is 1. This process is called normalization. This formula is actually a conditional formula. The calculation I just did was the probability of A intersect B or A intersect C given the probability of B or C. And the probability of A intersect B means we've got 1/3 and 1/2 plus the probability A and followed by the C followed by the A was a 1/6, 1/3, and the probability of B or C was that sum in the bottom that I referred to. And that's the crazy conditional formula. This restricted worldview look on conditional probabilities is a nice way to move forward. So let's do one of these restricted view looks on a probability. I am going to produce a test here. A test that talks about a sickness and a doctor trying to understand if his patients are sick or well. So sick, not sick, test positive, test negative. Now I'm going to not use probabilities. I'm going to use empirical numbers here and deduce probabilities from them. So let's say if it tests sick, it's 190 positive, and if you're sick and you test negative, it's 60, that's 250. And let's suppose that you're not sick when it tests positive. I think I have a number here I want to make sure. Yeah, let's do 50. That'll be 240. And then the other one I'm going to put in a 700 here. So this will be 750, this will be 760, and either way we add it will be 1,000. Now, there are some conditional probabilities here that can be calculated directly in a restricted universe. So let's do one of them. Let's do the probability that you're sick given you've tested positive. Well, given you tested positive says you live in this world. And the probability of 6 is 190 out of 240. Now, the probability that you're not sick living in that world would be the complement of that, which would be 50 out of 240. Let's do another one. Let's do the probability you're sick given you tested negative. Okay, this row, sick, 60 out of 760. And the probability you're not sick given you tested negative would be 700 out of 760. Now, I've calculated these numbers. I hopefully did them right. 190 out of 240 is somewhere in the area of 77%. That means this is in the area of 23%. 60 out of 760 is around 7%. And 700 over 760 is around 93%. The fact if they're exactly right are not relevant. I just want you to look at how a doctor might interpret this. Doctor gets a patient, decides to test for whatever reason, and out comes this data. I want you to notice that this one is a really solid thing to have happen. Doctor gets a negative back, and God, he's 93% sure it's you're not sick. This looks like a very good test for exclusion. Let's consider why that's nice. You've got several symptoms. They may be one of two diseases. It turns out this disease test isn't really good for saying you're sick because, good 1/5 of people aren't sick when it says positive. And let's suppose one of those diseases might be life-altering, but the other one is, let's find out you don't have it. So if he tests this one first and gets back a negative, he's very confident. Okay, now we got some other tests to follow up to look for things. But by excluding this disease with this test, he's in good shape. But if a plus had come back, he may not be willing to conclude that you have it. So there are tests for inclusions, the tests for conclusion. For example, most monos tests, if you test positive, it's like a 99.9% chance that you have active mono, provided something is going on. Some people, their mono test will always come back positive once they've had it. The Barr-Epstein one can be very long-term antigen remaining in your body. So they have to be used carefully. Now back to this picture here, there's a couple of things that are not good. This one and this one. Getting a test back and you're comfortable with it, and all of a sudden it says you're sick, but it's knowing that you're sick for some reason, but you tested negative, or you tested positive and you're not sick. These are falses. False positive, false negative, and doctors have to be very wary of them. This is why when they do some tests, they'll do, I'm going to do a couple more tests. They want to feel very comfortable that they've used conditional probability well. It used to be the HIV test done long ago produced lots of false positives, but it produced very few false negatives. So if a patient early on was showing signs of HIV, which back before we had interferon and other antiviral agents, it could have been a high probability of a death sentence. They were very happy that you were excluded. But if it was positive, they were not sure you had it. We later developed some very good HIV ones where HIV positive was a true test of confirmation. It was 99.99% correct. Now, there are many tests that like this, and I always tell my students that the pregnancy test, that little test where they get a plus, minus, plus, minus. The first one is called the control, and it must produce a plus so that you know the stick is functional. The next one is for pregnancy. The strange thing, plus means you're pregnant or you have high enough hormones in your body that you can say, yeah, I'm probably pregnant. However, the minus does not mean you're not pregnant. It simply means at that moment, this form of test doesn't confirm pregnancy. In fact, it is never a proof of exclusion unless you are months and months and months into a period of time where it's potentially you could be pregnant. But still your hormone levels could be low that it not triggers it. A pregnancy test that works like this, the P tests, unfortunately, only tell you you're pregnant very, very accurately if you have a plus plus. None of the other tests tell you anything. It simply says, I don't know. That's really strange. Now, there are several questions that we did. But there's also these questions. All of these probabilities are different. I recommend you go through a table and calculate each one of these conditional probabilities. Some of these are the universes of row, the others are the universes of columns. Hint, as I wrote it before, the universes are rows, and here the universes are columns. When I say the universes, those are the restricted universe. If you calculate them in the whole world with intersections and divisions, then the universe is the entire picture. All right. So this thing called conditional probability has a very nice formula. And it can be calculated directly by formula, but formulas, whether they're applicable or not, are always tenuous. You don't know the right way to calculate certain problems, and sometimes many problems have many ways of doing it. But I want you to notice these two are very similar, and this is in common, so this gives rise to a different kind of formula, that the probability of A given B times the probability of B is the probability of B given A times the probability of A, which says that reversing conditionals is a related fact. Now, if there are many different sets within a situation, this formula can get quite complicated. In the future, next section, we're going to go over Bayes' theorem, which is a pushing of this envelope to a future calculation. Now, conditional probabilities happen to be very nice. First off, they're all greater than or equal to 0. If you have disjoint events, then the probability of AI or AJ given B is just the sum of those two pieces. So mutual exclusive events add up. And more importantly, if you add up all where the union of all of these guys, disjoint union, they're all disjoint from it, is the universe, you're going to get a 1. This says that the statement of conditional probability is in itself a probability universe. It's a restriction of a larger universe, and you can talk about probabilities solely within that universe, and you still have nice probability calculations. You can restrict within that universe, and nothing truly fails you. This is really nice. It simply says that conditional probabilities work out great. Now, there's one strange thing. What happens if the probability of A given B is just simply the probability of A? In other words, B didn't affect A. Let me give you an example. What's the probability second birth in a family of a child is a boy, given that the first one was a girl? Basically, we say the second birth of a family is pretty much 50-50, just like the flip of a coin. What's the probability the third flip of a coin is a head, given the first two are tails? Well, it's still 50-50. Hasn't changed. So when this occurs, we say A and B are independent. Well, this leads to the following formula. This equals that, or the probability of an AND is the product of the probabilities. Independent process is a simple multiplication. This often happens in sequences of choices where one choice really does not affect the other choice. All right, so now I'm going to take a look at it. I have a device. It's made of two components, component 1, component 2. They're not really independent of each other. They're kind of glued together. Let's say they have a common heat sink or something. And the device operates for some limited time, fixed limited time. If C1 works, C1 and C2 works, or C2 works. In other words, just one of the two components has to be working for us to say the device is operating. Frequently, these are called backups. Now I'm going to make these backups not independent of each other. In other words, let's suppose C1 has failed. I'm going to make the probability of C2's failure a little higher because of the failure of C1, and vice versa. So ready? First, I'm going to say the probability of C1 fails, 0.01. And I'm going to say that's the same probability of C2 fails. But then I'm going to say the probability of C1 fails given C1 failed. I'm going to make that 0.03. And I'm also going to make the probability that C2 fails given C1 failed also to be 0.3. These conditional probabilities are often empirically measurable. You can design and build things and then you play them and see what happens. Because of this, you have conditional probabilities in your hand. How does a picture come out about this? Well, let's take a look at the device and let's follow C1 fails, not C2, C2 failed, not C1. And let's make an assumption they can't blow up and fail exactly at the same time. So this is either one or the other. So if C1 failed but not C2, that's a 0.01. If C2 failed, not C1, that's a 0.01. Now, from this, we conclude that C1 and C2 are functional. Why? That's got to add up to 100%, so that's like 98% of the time. We're not going to worry about that. Now I'm going to go on to this one. The probability of C2 failed. Given we've gone down this path that C1 has already failed. Well, this is a 0.03. Well, this is a 0.97 then for probability of C2 works, given C1 failed. Well, now we're going to continue. Probability that C2 failed, and now probability of C1 failed, given C2 failed. That'll continue with a 0.03. And then here's C1 works. I'm not going to worry about these over here because I'm more interested now that I have this semi-redundant system. One failure can affect the other. I can ask myself, what's the probability the device fails in some limited period of time? This, whatever, define this. Well, that means we want to ask, what's the probability of reaching here? And what's the probability of reaching here? Why, that's the following. It is the probability that C2 failed given C1 failed times the probability of C1 failed, because we went down this chain to get here, plus, and now we're going to go down that chain, the probability that C1 failed given C2 failed times the probability that C2 failed. And we're starting to see that large problems can be described in a sum of conditional probabilities and other calculations. This works out to be 0.0006, so it's a pretty small situation. By the way, this is called case studies. This is case 1. This is called case 2, and they're independent of each other. One can't happen when the other one happens. So what's really interesting about this is that this type of calculation is an exhaustive, independent breaking up of the description of a universe that we're interested in. Now, conditional probabilities are lots of fun when you incorporate them into games. Like, what's the probability of getting a blackjack given that you just got dealt a 10? Or what's the probability that you're going to get a sum of 7 given you just shook a 2? These are kind of neat probabilities. So I'm going to introduce you to a very specific probability model that we like. And this is a non-replacement, unordered, calculation. So this is two of its fundamental principles. I'm going to generate it in terms of a deck of cards. We have 52 cards. I'm going to what we call deal a hand. My pen seems to be dying here because I've done this lecture 7 times. No, it's actually the 5th. Deal a hand, and I'm going to have that hand be 5 cards. This hand is unordered. And I'm now going to ask for certain things to happen. So let's do the following calculation. What's the probability you get dealt 3 kings? Now, this model is an equally likelihood model. We claim that we can deal 5 cards, that you got a hand. If we do every single one of them, they're all equally likely. So the all ways, remember the number of ways over the number of all the ways, is an equally likelihood probability. So how many ways can we deal a 5-card hand? Well, we use the combinatoric rule, 52, choose 5, because it's unordered. So there the hand is unordered. That's the total hands deliverable. Now I'm going to ask, how many ways can I actually be dealt 3 kings? Well, you get dealt your hand and just ignore the non-kings. Well, you know you have 4 kings in the deck, and you somehow chose 3 of them in your hand. That number is 4, and it's pretty easy to see. King of hearts, king of diamonds, king of spades, king of hearts, king of diamonds, king of clubs, king of diamonds, king of clubs, king of spades, and that's a heart, heart. So this is not heart, so we need a king of hearts, king of clubs, king of spades. This is the not club hand, this is the not spade hand, this is the not heart hand, and this is the not diamond hand. That's a nice way of saying it in a negative format. There's 4 of those. But once you get the 3 kings, well, there's 48 other cards in the deck from which you're choosing 2 of them to complete your hand. So here's a probability of being dealt 3 kings. I'm going to close this with a very simple question of you that I want you to think about. It's not your homework. I'm going to email that. I'd like you to do the probability you get 3 kings given you peeked at the first card and it's a king. Can you do that? By the way, this probability calculation here is called the hypergeometric. It's a wonderful calculation. I like you to notice that the 4 and the 8 add up to 52, the 3 and the 2 add up to 5. We're going to be working with this probability calculation frequently. All right. Well, 5th time's a charm, let's see.